Lesson 8507, Feel the Burn, Comparing Representations of Functions. In this lesson, we'll describe the strengths and weaknesses of different representations of functions and compare inputs and outputs of functions that are represented in different ways. In the activity done in class, you won't see it as a slideshow in Desmos this time because it was a different kind of activity, but we compared 3 people burning calories, where one was represented with the graph, one was represented with the table, and one was represented with an equation. All right, we're on page 23 in your notebook, and our learning goal for today is to compare inputs and outputs of functions that are represented in different ways. Compare inputs and outputs, oops, just space there, of functions that are represented in different ways. And there's lots of ways to represent functions. The 3 ways that we've seen a lot are tables and equations and graphs. We saw all 3 of those in the activity that we did in class, but for these notes, we're just going to examine 2 types of representations in relation to each other. So let's take a look at our scenario here. We have Elena opening an account on the same day as Noah, a bank account. The amount of money, E, in Elena's account is given by the function E equals 8W plus 70, where W is the number of weeks since the account was opened. And the graph shows some data about the amount of money in Noah's account. Whew, okay, there's a lot of things going on there. But just like in the activity that we did in class, we're comparing 2 things, or 2 people in this case, where the representations of their functions are a little different. We have Elena, and the amount of money that she saved is represented by an equation. And we have Noah, and the amount of money that he's saving is represented as a graph. But we still have the same 2 variables for both of them. W is the number of weeks since the account was opened, and then the other amount is how much money they have in their account. Let me see. The amount of money in Elena's account, and we have the amount of money in Noah's account. So even though they're represented in different ways, an equation and a graph, we can still compare them. They're still functions with the same variables. Let me show you what I mean. For both of them, we can answer this question: who started out with more money in their account? I'll explain how we know here. Well, let's look at Elena. E for Elena. All we know about Elena is this equation, but it's enough for us to figure out the amount of money in the account when we started out. Well, when we started out, that means that no weeks have passed yet. So the number of weeks are equal to 0 when we're starting out. So let's use that in this equation. So 8 times, well, we've had 0 weeks so far, plus 70. Well, if we simplify that, 8 times 0 is just 0, plus 70 is 70. So that means that the amount of money in Elena's account is $70. Well, we can find the same information for Noah. We're just going to find it a little differently. We'll do N for Noah here. All we have for Noah is this graph, but we're still going to be looking at 0 weeks since opening the account and figuring out where our graph starts for Noah. So at 0 weeks, let's come up here. It looks like right here is where we have our first data point. So if it were a coordinate, we have 0 weeks and 60. That's the amount in his account. That's the coordinate right there. So Noah has $60 to start at 0 weeks. So we can say that Elena has more money at the start. at 0 weeks. All right, so different representations, but we can still compare them. Let's move on to this question. Who is saving money at a faster rate? Okay, well, this is going to be about rate of change. We can tell rate of change from either an equation or from a graph. Let's see how we can do that. So again, all we have from Elena is this equation, but this number is the rate of change. That's how much her account is changing every single week. So every single week, there's another $8. $8 per week. So we found the rate of change for Elena. Let's find the rate of change for Noah. Well, for Noah, the rate of change is really like the slope. So I'm going to look at 2 points on this representation here. I'm going to make myself a little slope triangle and look at the height and base to find the rate of change. I just have to make sure I read the axis here really carefully. It looks like the height is $10. Each of these boxes represents 10 on this axis. And the base of this slope triangle, 2, 3, 4, is 2 units long. So he saves $10 every 2 weeks. So the slope is going to be the height of that slope triangle over the base of that slope triangle. If it's $10 in 2 weeks, looks like we have $5 in 1 week. Okay, let's just put that over here. So $10 in 2 weeks means we have $5 per 1 week. Now, again, it looks like Elena is saving at a faster rate. So she has more money to start and she's saving at a faster rate. Elena looks pretty fortunate. Okay, but we're proud of Noah as well. They're both saving money, good habits. So that's the point of this lesson, is taking 2 different representations and still finding a way to compare them. Different representations have different benefits. I'm going to talk about the benefit of each kind of representation down here, and then we'll come back to these questions that might be more easily answered with one representation over another. Let's start with a table. We didn't have one in the notes here, but you've seen tables before. And they're good if you want to focus on a specific input-output pair. We saw it in the activity in class today, where we had a chess champion and we saw after 1 hour how many calories he burned, after 2 hours how many calories he burned. And there were just lots of specific input-output pairs to look at. A graph is good for general trends. Oops. Like, where is something increasing? Where is something decreasing? Where is there no change? And if we have 2 functions graphed on the same graph, it's really helpful for comparing 2 functions, 2 or more. And finally, an equation is helpful for predicting the future. You're not really limited with an equation. And finding precise input-output pairs, whatever you want. In a table, they've already chosen those input-output pairs for you. But in an equation, you can plug in any input you want and find the corresponding output. It doesn't have to be a nice round number. It can be anything. So with these things in mind, let's go back to these questions. Going back to Elena and Noah, write a question that might be easier to answer using the equation than using the graph. Well, let's talk about predicting the future. That's something an equation is more helpful for. We could ask the question, How much money will there be in the account in 20 weeks? How much money will be in the account in 20 weeks? Well, I could answer that by just substituting 20 in for the weeks in this equation. That wouldn't be any trouble at all. But for the graph, if I wanted to go out 20 weeks, I'm kind of in a pickle here because it looks like at about 14. So this is helpful with an equation. A question that might be easier to answer with a graph, well, if we're looking for big trends, I might want to ask, is the money in the account increasing or decreasing? Graphs are just so visual. If it's going up from left to right, I know that the amount of money in the account is increasing. I could figure it out from the equation that Elena had, but it's not visually obvious, that general trend. Question mark here. So those are some of the benefits of different kinds of representations of functions. And as long as we have the same variables that we're working with in both representations, you can compare different people or different situations, even if the representation of that function is different. Good luck on that homework tonight.